Myself, Srinivasan, working as a faculty in the Department of Mechanical Engineering at Shishimawa College of Engineering and Technology. The last lecture we discussed about autoencoder and autoencoder architectures and how it is useful for nonlinear dimensional reductions, and these things we have looked at. So today we are going to look at reconstruction losses. If you look at this, these are all the input layers, okay? And this is the latent representation that we have already seen. This is our this is a reconstructed output from the latent representations. So basically, we could be able to see there are 6 features, and I can say there are 6 features in the input, and I can assume that there are 100 data points. Okay, let us take in this way. Suppose we have 6 different features, and 2, 3, 4, 5, and 6. There are 100 data points, for example, I should say. So the size of the one is that 100 into 6. And the lattice representation, for example, in latent representations, I could say that there could be 100 features into 3. So the size has been reduced because it is a compressed, in encoded it is a compressed form, and it has been reduced from 6 features to 3 features. Okay. So based on this, how many input parameters will be the input? I mean, how many weight? What is how many weights are between this input and hidden? So if you look at this, this is a matrix forms. I can say that the WE matrix would be, for example, into 6 into 3. This is a matrix form, so I can say there are 18 parameters. So totally there are 18 parameters between the input layer and hidden layer. Okay. And whatever that in encoder form, in the decoder form, whatever that latent representation that we have, it is compressed form of input image that has many important features that will be reconstructed here. This is a reconstructed zone. Okay. So the number of so when you reconstruct the image, and you will end up with whatever the size that we have initially we have. So the singularly it is going to be 6, and the input parameter is going to be 3 into 6. Here 6 into 3, and here it is going to be 3 into 6. So that is the way it works out. Okay. So basically, when we have the input image, and we will try to get some important features, and from the important feature again it is going to be a reconstructed one. So what is why it is doing? Basically, it doesn't memorize anything. It tries to learn on its own. That is the advantage of autoencoder. This can be used for the dimensional directions, for the non-linear. For us, PCA does only for the linear data. That autoencoder does for the non-linear data. So that is a use. But when we reconstruct, we lose some information. So that can be represented in this way. So this is a loss per sample. So the square difference between the input and the reconstructed one. This is a reconstructed one. Okay. This is for the single data point. Okay. So when you go for the loss, it's for the whole sample. So that's why we put 1 divided by n. So number of in this case is going to be 100. So it depends on the case it depends on the problem. It varies from one case to another case. So the number could be anything. Okay. So that is the loss can be calculated, the square difference between the constructed image and difference between the constructed one and the original one. Okay. So what it did in the encoded part, what it does is basically this is a latent representation. This is our input features, and this is basically our weight matrix, the encoder forms. So when we go for the reconstructed one, y x hat, it is going to be that the multiplication of this hidden representation and the weight matrix of this. So weight matrix of this. Okay. So that is going to be your reconstructed one. So always in reality it should be same, but it is not going to be the it is not going to be the same image that you get after reconstructions. So obviously there will be some sort of loss will be there. Okay. So when you substitute this value, in this case, and what will happen? X, WE and WT. WE is basically the weight matrix of encoded part. The WT is basically weight matrix of decoded part. Okay. So as I said, this is basically how it has come. And WD is basically 6 into 3. When you transpose, it is going to be 3 into 6. Okay. So this is a tied weights, I can say. And basically this objective function is to reduce the reconstruction error. Okay. So how we can reduce the reconstruction error? To optimize the weights. So to optimize the weights, if you optimize the weights, you will be able to reduce the reconstruction error. Okay. So this, when you have these tied weights, it can reduce the parameters and it can generalize well. Okay. So in order to not to prevent overfitting issues, we can use this, as we have seen. This is from regularization parameter. This is called regularization parameter. Okay, when you apply this lambda, then when you apply this regularization parameters, and what it does is basically it tries to prevent the overfitting and keeps the small weights. So as a result, you will be able to reduce the reconstruction losses. Okay, so basically once you get this training, and you will have the optimized weight. That optimized weight will give you the less reconstruction loss. Okay, so that is advantage of getting optimized weight to get minimum reconstruction loss. Okay, so what it does in the autoencoder is basically it tries to have this preserve the maximum information in the encoded part, and it tries to reduce that reconstruction loss. So that is the way it works out. Okay. So what we have seen so far is that what is the architecture of autoencoder, and how we can calculate the reconstruction losses, and how we can reduce the overfitting issues in the network. Okay, thank you. In the next class, we will look at various types of autoencoder. Thank you.